Hello, my name is James Hill, and I'll be presenting our paper titled Using Multi-Core Architectures to Improve the Performance of Real-Time Dynamic Binary Instrumentation. This work was done by one of my former master's students, Mike Dew. So just to get started, just to give you context of what this paper is about, it's about the area of dynamic binary instrumentation. Dynamic binary instrumentation is a form of non-intrusive instrumentation that rewrites the binary to gather instrumentation data for analytical purposes. Now, we say non-intrusive, we understand that all instrumentation is intrusive. By non-intrusive, we're talking about having to interact with the actual designers of the system, the developers of the systems, the engineers of the systems. In intrusive instrumentation, you're modifying the source code to collect what you need. So it requires you to intrude on the developer's normal development lifecycle to gather data you need for analytical purposes. And as that system evolves, you must also evolve the instrumentation code to continue collecting data you want. In a non-intrusive instrumentation situation, you're not modifying the source code to collect what you want. And so one area of this that allows that is something called dynamic binary instrumentation. As I said before, what it does is it rewrites a compiled binary so that you're able to gather information from the system for analytical purposes. One thing we do know about DBI is that it will add varying amounts of overhead to whatever application you're instrumenting in real time. And a lot of that depends on how much data you're trying to collect. Okay, no matter what tool, whether it is a tool which we're going to talk about called Pen or Solaris dtrace or Dynamo IRO, all these tools, even though they can be used in production, they still add some kind of instrumentation overhead to the system. Now, active area of research within these tools, of course, is how do you reduce this instrumentation overhead? And there are various techniques out there that already exist for reducing the overhead generated by DBI tools. A lot of those deal with data buffering and analyzing it on a separate thread, buffering and doing post-mortem analysis, or dumping the data to a local drive or to your local disk at well-defined intervals. Some people have even looked at how you actually can clone an application and run them both in parallel, where you're running real-time version and a clone of the application, and trying to instrument the data that way to reduce the overhead and so forth. And again, one thing we see that a recurring theme of this is that they're trying to use just whatever cores they have available to try to reduce instrumentation overhead. But one things we realize within the existing solutions is that they're limited to a single application running on a single host. But this presents a challenge when you're talking about a distributed system where you have software running across many different nodes in real time. How can you collect this data in real time and analyze the data in real time? And so within this, we came with an approach for our tool called REBIS, which basically has this twofold approach where we look at one is how can we find other techniques for reducing instrumentation overhead within a single host, but then also find a technique that allows us to offload data in real time from multiple hosts, and hopefully it's lightweight. That way we can do real-time analysis or get closer to doing real-time analysis of distributed real-time embedded systems using DBI tools. And so the background of our research sits within two types of technologies. One is called Pen++, and Pen++ is a framework that we have developed a couple years ago. About 5 years ago, we developed it. And its aim is to reduce the complexity of pen tools and make it easier for developers to author analytical tools for a dynamic binary string tool called Pen, which is released by Intel. The Pen tool supports all x86 architecture, and again, is managed and developed by Intel. And so Pen++ is a framework that sits on top of that and uses template metaprogramming. And we've shown that through various extensive of testing that it can reduce complexity, it can improve performance of pen tools, it can improve modularity. So therefore, it gives you a framework where you can do a lot of get a lot of reuse from existing code and solve problems and reuse the solutions that you've created from other problems on newer problems or extend them as easily, or having to reinvent the wheel. Because before Pen++ came out, writing a pen tool was very, very hard to do. And also, we are using a technology or a open standard called binary JSON. And we'll explain basically the reason why we're doing that is because we were trying to find open standards that were lightweight, easy to use, and that would help us streamline the network communication as opposed to some of the existing technologies that already exist, such as DDS and Core, which you will hear about in a few. So several design challenges that we faced was, and you'll see why we end up going to the BISON approach, is that we wanted to try to leverage some existing technologies that are already used in real-time embedded systems, distributed systems, and so forth. One was DDS, and we tried to do it with OpenDDS. And one of the challenges we found with OpenDDS was that when we tried to compile OpenDDS into a pen tool, it wasn't compatible on Windows, in a Windows environment. There were numerous compilation errors that were outside of our control in terms of how things were linking and trying to resolve symbols, because Pen has its own runtime architecture as well. It's a virtual machine. And so trying to get things ported over to compile within Pen just was not working out. And so then we actually stripped down OpenDDS and said, well, since we can't use DDS, which can give us that pub sub behavior we're looking for, we wanted to say, okay, well, let's look at another technology that exists called ACE, which people may be familiar with, the Adaptive Communication Environment. ACE is actually used under the hood to implement OpenDDS. And so we were like, let's strip away all the pub sub stuff and just get it down to ACE, since ACE provides the abstractions for doing network communication. And it would take away that complexity of the application from us. Right. And so we tried using ACE, and we found out that, in order to get ACE to work, we had to port over its mutexes and its threading framework. But in the process, there was not really a clean port. But more importantly was that when we finally got it to compile correctly, which we were able to do, when dealing with all these namespaces and so forth, that how ACE does to prevent collisions, when we finally got everything ported over to the Pen runtime architecture and to the Pen framework, trying to actually run the tool caused sec faults. And it boiled down to basically how ACE deals with static variables and initialization, and Pen did not like that. And so we could not actually get around that problem. And so we had to actually scrap using ACE as well. And so for that reason, that's why we end up having to write our own networking library ourselves. And we end up basically using binary JSON to do that. And we use binary JSON because it was easy to develop a networking protocol on top of that. Also, is very extensible too with user-defined types, which you'll hear about in a few slides later. And so when we designed this technology, REBIS, what we ended up doing was we took advantage of the idea of trying to run stuff on many different cores, unlike what people were doing where they're just trying to just dump the data. We wanted to try to use those individual cores to try to offload data to a shared server that is basically over the network that all the different hosts can communicate with. And so we ended up doing basically in our design of REBIS was that anytime a thread comes online, an application thread comes online, that thread is basically bound to one of the cores that exist in the system. Okay, and then we have several cores that are actually bound for instrumentation purposes. And so what you'll see is that if you had a set of, say for example, you run a 48-core machine, 2 or 3 of those cores may be designated just for instrumentation purposes, for collecting the data and offloading it. Right, the other remaining 45 cores will then be used for any application threads. And there is actually various scheduling algorithms that we strategize that you can put in like round robin so that it will basically use those other 45 cores for running application threads and keep those other 3 cores separate. Okay, when each instrumentation thread comes online, right, within each instrumentation thread, they're all given their own buffer. Okay, and each time we give them their own buffer, most because we're trying to prevent there from being any types of locks. We're trying to minimize the amount of locking that has to occur as you're reading and writing to these buffers. Okay, And then lastly, you have these analysis threads. Analysis threads basically is their sole purpose is to just take the data that's in the buffer and then offload it to the server. Okay. So basically, you have these different types of threads. You have instrumentation threads that are there's one instrumentation thread that corresponds with an application thread. It has its own buffer. And then you have analysis threads, which are bound to the cores, to the instrumentation cores. And its sole purpose is just to offload the data that is collected in the buffers to the server. And so again, the whole idea behind this is to try to minimize the amount of locking that occurs. And again, just to help minimize the amount of locking that occurs as well, is that the buffers are actually using a double buffering technique. And so while one instrumentation thread is filling up a buffer, analysis thread is actually taking a previously filled buffer and offloading that to the server. So again, these are just little techniques we're doing to try to minimize the amount of locking that's occurring in the system. Now, when it comes to our networking library, like we said, we did a implementation of binary JSON, which we call BISON. Okay, and there is an open source implementation called Project Canal, which you will hear about in our results. And there is a legacy implementation which comes from MongoDB as well. And unlike those two implementations, what makes ours different from a feature that makes ours different from those is that BISON or binary JSON says you can support user-defined values, but the current implementations of those two technologies don't let you do that easily. And so because we know that we're instrumenting applications, and there may be a situation where a analysis tool, pan analysis tool, may want to send some type of custom data type over that's not a built-in type that we don't support. And so they may need a way for them to, we need a way to provide for this author of this pen tool to be able to add that custom value to the binary JSON implementation or instrument over the network. And so what we have here basically is we have a way of adding user-defined types via basically just factories and a value interface that the pen tool or the pen tool author will have to implement. And once they implement this factory and this actual value, then they'll be able to add their custom value to the BISON so that we can serialize and deserialize that value, that instrumentation value they want to instrument. And again, this is only if they they need a custom type that's not supported via some of the built-in types that come with binary JSON. So now let's get into our experimental results of the system, right, with REBIS. And so what we did was we did our evaluation of our implementation. All of our experiments were done in an Emulab installation that we have at IUPUI. All our hosts basically were AMD quad-core processors running Ubuntu. We had everything connected via virtual LAN, where the average round trip was basically 0.1 milliseconds. And we used pin 2.14 for our testing purposes. And we also pulled in again, like I said, we found two other implementations of the binary JSON implementation. One was Project Canal, and the other was the legacy MongoDB driver. And for those who know, MongoDB actually uses binary JSON to store and retrieve data from its document model. And so first we looked at basically the marshalling, which is basically us writing data to the network, okay? And so the way this graph goes is what we did was we went and basically tested all the different data types that come with binary JSON. And so again, binary JSON, is types, unlike JSON, they do have types in there. So you can actually say what type is that data value, which makes it easier to parse, okay? And so the way this graph reads is that we were looking at, the numbers 1, 100, 10, 100, and 1000 represent the amount of elements we were writing or reading or whatever we're doing with that particular type of test. Then we have bars, the chunks of bars, the groups represent the different types of testing we were looking at, the different implementations. So for example, a baseline, one that had memory pool, one that was not doing any copying the implementation. You have memory pool plus no copy. Those are our implementations for BISON. You have the Project Canal, and if the 6 bar exists, then that's where you have the MongoDB implementation. Okay, and so what we see basically here is when it comes to writing, basically, for simple types and so forth, right? We had the fastest results. The no copy had the fastest results for BISON out of all implementations, and the memory pool produced the slowest results. But it came right here, for our implementation, the BISON, it outperformed Project Canal, which is the other open source one that exists. But the MongoDB was actually the fastest in terms of writing data types to the network and serializing. When it came for searching for elements in the system, right? Searching, so you have this document comes over, you want to search for something inside the data, okay? Our BISON, basically, our baseline and with all the different optimizations, they pretty much perform pretty much the same. So it shows that, really the optimizations really weren't helping too much with the searching. But when it came to the MongoDB, it performed the worst for searching. And that's basically because of how MongoDB's algorithm works when it searches through the data and so forth. And then Project Kanai, we perform a little bit slower as the project from Project Kanai as the amount of elements got more. Document marshaling, basically it showed that Project Kanai had a lot of failures, and so we couldn't really get accurate results when it came to that and so forth. But usually the mempool, it did much better when it came to large chunks of data, when it came to our results and so forth. And when it comes to deletion of elements in the data set itself, the mempool performed a little bit better. A lot to do with how we are recycling the objects. But MongoDB was the fastest for one element and got slower. And as you have more elements, that's basically how MongoDB is doing its deletion, where it's basically saying delete one, and then it's and it's trying to reuse the original document as well. And again, Project Now was the slowest implementation. Then we actually looked at a networking performance, and this right here we're trying to see basically how much as you're sending data over the network, how does it fare? As you see, of course, it's like it's going exponentially. And the reason why is because is that the INS count is the most intrusive implementation, and the malloc MT is one of the most coarse-grained implementations or instrumentations, where it's just looking at just routines, where INS count is counting every single instruction. And so we're seeing that basically, as it gets more intrusive, we are definitely seeing net performance actually become worse, which is increasing. And that's expected, right? And so we said, well, can we actually do some kind of prediction based on this? And so one thing we found out was that if you were to take all the different results we did, we looked at message received and increase in the runtime, we're able to plot those out and come up with a R squared of 0.85. But we found out that the proc count was kind of like an outlier. And if we remove that from our analysis, then we get an R squared of 0.99. And so this kind of basically means that we thought this was very promising, because it shows that our implementation, even though it does add overhead, is that if a person understands how much they have to collect, then they could potentially predict how much overhead they'll be adding to the system when they're using the REBIS technology. And so lastly, we looked at CPU binding to perform results without the CPU, because we try to bind CPU cores so we can reduce instrumentation, or bind the analysis instrumentation to different cores to reduce instrumentation overhead. And one thing we found out basically is that, as the application spawns more threads, you need to have a much larger buffer. That's what we're finding out. And also we found out that CPU binding doesn't really have that much effect on situations. Buffer size doesn't really have too much effect on the CPU binding, right? And so this is really important when you get into places where we have limited memory and stuff, right? But one thing we are definitely find out is that there is an impact when you do actually add CPU binding. It's just you have to understand really how much data you're collecting, how many threads are running, and that can help you understand how you have to actually you do your binding. And so just into concluding with just to finish up, is that, in this paper, we talked about basically approach for, dealing with data buffering and binding instrumentation analysis threads to different CPU cores to try to reduce overhead. And we also introduced a lightweight analysis routine for offloading data via the REBIS technology. One thing we found out was that, we were able to taking the most intrusive pen tool from pen, we were able to get it run 11 times faster than the naive one that comes with the pen manual with this approach. And we also found out that, one analysis thread can handle at least 3 instrumentation threads when collecting data after, every application instruction. And that's when it's very, very intrusive. So it means that the less intrusive you have, then you can actually have more analysis, more instrumentation threads being used with a single analysis thread. Again, it comes on having to do more, analysis on your end to figure out, how much data you're collecting, how many threads are running, and then hopefully we'll be able to you'll be able to figure it out. And in the future, we hope to be able to actually be able to predict how many threads or how many analysis threads you will need based on how much data is coming in and how many instrumentation threads are running. Thank you. At this point in time, we take any questions.